Okay, activated complex theory is an alternative modern approach to the collision theory in which it is used to explain the mechanism of a reaction. So the fundamental postulate of this activated complex theory is that the reacting molecules must form an activated complex before being converted to products. And there will exist an equilibrium between the activated complex and the reactants. So the major features of this activated complex theory are the reacting species must come into contact before the formation of the activated complex. The potential energy of the system along a path connecting the reactant state to the product state contains a maximum. So configuration of atoms of the two species in contact at this maximum state is called activated complex. So if you look at this graph here, okay, the plot versus potential energy versus reaction pathway. So this point here is the reactant. Okay, so it must come into contact before it form the activated complex, means at the maximum this point here. Okay, then product will form after the formation of activated complex. Okay, in this example here, this is rearrangement of methyl isonitride. So this is the methyl isonitride. So during the rearrangement in this transition phase here, okay, you can see the triple carbon bond is starting to move, okay, from the 180 degree position. Okay, so it moves inwards, okay, before it reaches the maximum point, which is the activated complex, and it becomes like this. Okay, then product will form. Okay, so that is how to visualize what happened during the colliding reactant to form product. Okay, in this case it's rearrangement. Okay, this diagram shows the energy of the reactant and also the product, and you can see this point here indicate the change in terms of energy between the reactant during the formation of product from reactant. So the high point in this diagram, which is here, is the transition state. So the species present at this transition state is called activated complex. So you have to know the difference here. Okay, the position here is called transition state. Okay, the species present at this transition state is called activated complex. So the energy gap between the reactant and the activated complex is the activation energy barrier. Okay, here. Okay. So consider reaction between carbon monoxide and nitrogen dioxide. Okay. So this is the reactant. Okay. Before the formation of product, which is carbon dioxide and also nitrogen oxide, it has to form the activated complex first. Okay, the highest point in the diagram. Okay. So the conversion of the reactant to product is through the formation of this transition state or activated complex in terms of its species. So the activated complex is a molecule in the process of breaking or forming bonds, and the atoms are linked together with loose valence bond. So this is the loose valence bond here, uh, the dotted line here. Okay, because the carbon um, from carbon monoxide here is going to form a bond with oxygen from nitrogen dioxide, and one of these oxygen, okay, from the nitrogen dioxide is breaking off. Okay, so this is the point of activated complex. Okay, this graph here shows the reaction between nitrogen dioxide and carbon monoxide just now. Okay, so these are the reactant here. Okay, and these are the transition state, and then products form. Okay, breaking off one of the oxygen from nitrogen dioxide here. Okay, and then that will form later on the bond between carbon monoxide to form carbon dioxide. So this is the transition state. This species here is called activated complex. So note, this is the activation energy of the overall reaction. Okay, this is the activation energy of the reactants. Okay, and this is the this is the activation energy of the reactant. Okay, in order for it to go over the barrier. And based on this activation energy of the overall reaction, okay, and also the reactant, we can calculate the enthalpy change, which is negative 226 kilojoule per mole. So the bimolecular reaction between a molecule A and B can be written as this. Okay, reactant A and B forming the activated complex at the transition state to form product. So the rate of reaction is equal to the concentration of the activated complex and the frequency of the decomposition of the activated complex. So we can write the rate law expression as this. Okay, negative d concentration A over dt equivalent to AB multiply frequency of the decomposition of the activated complex. So AB in square bracket here is referring to the activated complex concentration. Next, we move on to reaction mechanisms. So mechanism of a reaction will tell us the precise position of the atom in the reactant molecule as a function of time as they are converted into products. So it actually refers to the step, so if it involves only one step, or a series of steps by which the initial reactant interact in the process of forming the products. So most of chemical reaction take place by a sequence of steps, or we call them elementary processes. If you remember that we have discussed this in the early part of kinetic lecture. A reaction mechanism defines a chemical reaction as a series of elementary steps. So in elementary steps, the molecularity and kinetic order are the same. So if you remember, I have discussed this in the early part of kinetic. The molecularity, okay, and kinetic order are the same for elementary steps. For example, if we have A react with 2B, for example, forming C plus D. Okay, so the red law, okay, the red law will be based on A and also B squared. Okay, so the kinetic order here too will follow the molecularity from the balanced chemical reaction. So only for elementary steps. If not elementary steps, then we only can determine kinetic order from experiment. So example, as I shown here, is a bimolecular step. Okay, bimolecular step means we have two reactant. Okay, let's say we don't have two here. Okay, we don't have two. Okay, so this is bimolecular reaction. So it's a second order because the total order here is 2. So the rate determining step, or also known as slow step, is one of the elementary steps in the mechanism. So each elementary step would have a hypothetical species which was too short-lived to be detected using instrument. These two short-lived species are the activated complex that we have discussed just now. Okay. So the process of bond breaking and formation during the activation, during the transition state, the process of bond breaking and formation of the activated complex at the transition state is so fast, okay, that these transition states have very short half-life. So because very short half-life, it is too short to be detected using instrument. Means difficult to be detected using instrument. So what is intermediate? Intermediate is a species that initially form in one elementary step only to be consumed as a reactant in a later step. So if you remember physical chemistry 1 has law, okay, you have series of step, right? Step 1, step 2, and then you have the overall reaction. So in step 1, let's say you have reactant A and B produce C and D, and C here is the intermediate. Okay, C, let's say only C. C is the intermediate which is used in the later step as the reactant. Okay, C plus E, okay, producing F, for example. Okay, so that's what it means by intermediate. So the intermediate species live long enough to be isolated so that their properties can be measured. So not all elementary reaction within the proposed reaction mechanism would have an intermediate. So elementary steps are classified by the number of reactants molecule that come together in a step, okay, which we call molecularity. So the molecularity of a step is always a whole and a positive number. Okay, it must be a positive number, it must be a whole number. So unimolecular means refresh back. So only one reactant molecule involved. Bimolecular, only two reactant molecules involved. Thermolecular, two reactant molecules. Not impossible, because it's extremely rare, like I have discussed in the earlier lecture. So the rate equation for the elementary steps is given by the product of the rate constant and the concentration of the reactants in that particular step. Okay, for example, here, this is our elementary step. A is the reactant producing product. Okay, so this in terms of molecularity is unimolecular because only one reactant. So it's unimolecular. So the rate law or rate equation is determined by the reactant itself. Okay. So the second one here is reactant A and B producing product. So this, because I have two reactants, it's a bimolecular reaction. Okay. And if we write the rate equation, so we consider the reactant A and B in the rate law. So A and A here producing product is also bimolecular reaction. Okay, so when we write the rate law equation, this is the expression for it. Okay, the last one is thermolecular because we have 2A and 1B. Okay, producing product. So the rate law or expression is based on the concentration of A squared and also B. Okay, note that the stoichiometric value here is used as the order of direction in the rate law. Okay, because it's elementary step. Okay, let us look at the example to determine rate law or rate equation for elementary steps. This is a two-step mechanism, okay, for the decomposition of ozone. Okay, so this is, if you see here, this is the overall reaction from this step 1 and step 2. Okay, so overall we have 2 ozone producing 3 oxygen gas. Okay, so step 1 is unimolecular, okay, because only one reactant, which is the ozone. Step 2 is bimolecular because it involves two reactants here, the ozone and also oxygen atom. Now, if we write the rate law for each step, because these are the elementary steps, so means we follow the molecularity. Okay, so this is the rate law for step 1. Okay, and this is the rate law for step 2. Note that the rate constant is written as K and K prime. So means they are not the same in terms of its value. Okay. Now, if the kinetic order is the same as the molecularity, then the balance equation is a good representation of the reaction path. So if you look at the example given here, hydrogen and chlorine, okay, producing hydrochloric acid. Okay, so stoichiometrically, 1 mole of hydrogen react with 1 mole of chlorine, and given the rate law is this. Okay, also following the stoichiometry from the balance equation. Okay, so means this is a good representation of direction path. Okay, the balance equation here, okay, is a good representation of direction path because the rate law follows the stoichiometric value of the balance equation. If they are not the same, okay, then a mechanism must be proposed. Okay, for example here, okay, formation of oxygen from ozone. Okay, so 2 mole of ozone producing 3 mole of oxygen. Look at the rate law here. Okay, the red law is not a good representation from the balance equation, because red law is different. Okay, it also have oxygen in the red law expression, whereas in the balance chemical reaction oxygen is not in as one of the reactant. Then mechanism must be proposed. If that are not the case, okay, means they are not in agreement with each other. So what is the purpose of a reaction mechanism? Okay, reaction mechanism is capable of predicting results under some specified environmental conditions. So a reaction mechanism will give a chemist a degree of control over the reaction process. So if we know how a reaction proceeds, then it is possible for us to control the reaction process, for us to obtain higher yield for a specific product. For example, a reaction involved in the formation of one isomer product under one set of condition, and yet another isomer product under a different set of condition. So we can control that. So the rate of the overall reaction is limited by and is exactly equal to the combined rates of all of the elementary steps. And of all the elementary steps, one of the steps should be the rate determining step, in which it is the slowest elementary steps of a sequence. So example here is reaction involving two elementary steps. So if you look at step 1, A react will be producing X plus M. Okay, so this reaction is slow. Okay, activation energy is large. Step 2, if you look at step 2, M here is the intermediate which is used as the reactant in step 2. Okay, to produce Y. Okay, to produce Y. So elementary step 2 here is a fast reaction. So we can find the overall reaction from these two step elementary reactions. Okay, so we have 2A here, 1A, 1A, so 2A, so 1B, 1B. So M is the elementary is the intermediate, so it's not reflected in the overall reaction. And then we have X plus Y here. Okay, so if you've done this in physical chemistry 1 class, okay, Hess law. So the overall rate is based on the rate determining step, which is the slow step, which is step 1. So we can reduce the rate law based on step 1, okay, which is K square bracket A multiply with square bracket B, okay, concentration of reactants A and reactant B. So because this is law, so it's the rate determining step for the rate law. So reaction where the first step is the rate determining steps is very easy, because we can deduce the rate law directly from the first step. Okay, if we look at another example here, reaction between nitrogen dioxide and fluorine, okay, to produce nitrogen dioxide fluoride. So this is the most likely reaction mechanism. Okay, so we have step 1, NO2 react with fluorine to produce NO2F plus F, and this is a slow reaction. Step 2, F is used, F produced in step 1 as the intermediate is used as reactant in step 2, react with nitrogen dioxide to produce NO2F here, and this is a fast reaction for step 2. So the rate law is based on the rate determining step, which is the slow step, which is the first step. So when we write the rate law expression, we use nitrogen dioxide and fluorine from the step 1. Okay, so this is overall second order. Okay, second order. First order with regards to nitrogen dioxide and first order with regards to fluorine. So this is another reaction example, okay, where the first step is the rate determining steps, decomposition of ozone to oxygen, and this is the mechanism proposed. Two-step elementary reactions. Okay, first step is slow step, followed by step 2, a fast reaction. So therefore, the suggested mechanism leads to the observed first order rate law. So the rate law is based on the slow step, which is step 1. So we write the rate law here. Okay, based on the rate term from step 1. Okay, this is another example, reaction between nitrogen dioxide and carbon monoxide at low temperature to produce nitrogen oxide and carbon dioxide. So it is two-step mechanism in which the step 1 is a slow step, followed by step 2, which is fast reaction. Okay, so when we write the rate law, we use the rate determining step, which is the slow step, step 1 here. Okay, 2 NO2. Okay, so NO2 squared. Now this is not the case if the first step of the mechanism is a fast equilibrium which produces an intermediate which later on react slowly in the rate determining step or the slow step. For example, ammonia cyanide urea reaction here. So this is the rate law for this reaction. Okay. The mechanism consistent with the rate law is this. Okay. Step 1, step 2. Okay. So look here. The first step is a fast step. Okay, which produces the activated complex or the intermediate, which is used as the reactant in the later step, which is the slow step. Okay, so when we write the rate law, remember the rule of thumb here is when you write the rate law, it has to be based on the slow step. So when you write the rate law based on the slow step, you would put NH4OCN, which is actually the intermediate or the complex, and it shouldn't be in the rate law. Okay, because like I mentioned in earlier on, it is too fast to be um, measured, okay, by instrumentation. Okay, so it shouldn't be in the rate law. So how are we going to do this? Okay, we have to use the fast equilibrium reaction in order to find the rate law. Okay, so what are we going to do is go back to the first step. Okay, so the first step is NH4 plus OCN minus. Note that the arrow is pointing at both direction. So when it's pointing at both direction, we have to consider both sides, which is the reactant side and also the product side. Okay. So when we write the expression, so K1
Okay, K1, okay, going forward to the product. So K1 NH4 OCN here. Okay, here. And then it will be the same as the reverse reaction, which is K negative 1. So when you reverse direction, now NH4 OCN becomes the reactant. So here. Okay. So we put the red constant K at one side. Okay, so we bring K negative 1 to this side, and we bring this to the other side. So that's why we get this. Okay, so NH4 OCN divide with NH4 OCN. So the fraction between K1 and K negative 1 can be written as K equilibrium. Okay, so now we want to replace the intermediate based on the rate law deduced from the slow step just now, right? It shouldn't be in the rate law. So we have to find what is NH4 OCN to replace the red law just now. Okay, so we put this one side and the rest on the other side. Okay, so we bring this to this side. Oh no, we just bring this to this side. So we have K equilibrium multiply NH4 plus OCN minus, leaving behind NH4 OCN on the other side. So we substitute this into the slow step or the rate determining step just now here. Okay, so we substitute this into here. Okay, this. Okay, okay, substitute here. So we have K2, K equilibrium, NH4 OCN, and we can write this as a new rate constant as K, and this is the rate law. Okay, which is the experimentally observed. So if you notice, if the slow step is not the first step, then you have to go through a lengthy way to solve it. Another example is nitric oxide oxygen reaction. This is the rate law. Okay, the rate law. So there are two possible mechanisms. Both of these mechanisms, set of mechanisms, consistent with the rate law that has been suggested, which is this. Okay, so let us look at the first set. Okay, the first set, first step is a fast at equilibrium, followed by step 2, slow step. So what do we need to do first is write rate law based on the rate determining step or the slow step. So means rate is K N2 O2 O2. Now note that in the overall reaction here, okay, there's no N2O2, means N2O2 here is the intermediate, which shouldn't be in the rate law. So we have to replace this. How to replace this? Using step 1, the fast step. So based on the first step just now, okay, we write the rate law expression like this, okay, because it's the arrow is pointing in both directions. So we have K1 and K negative 1. So this has been done for you. And then we put on one side. So we have N2O2 over NO squared. So we leave this behind. We bring this NO2 to this side. So we have N2O2 equivalent to K equilibrium and O2 squared. And we substitute this into the slow step just now, rate law. So substitute in the only substitute NO2. Let me just write back the rate law based on the second step just now. We have rate equivalent to K into So we only substitute this N2O2 with this expression here. So this one goes here. Okay, so that's why we end up getting K2, sorry, this one K2, K2, K equilibrium, and then N2O2 is equivalent to K equilibrium NO squared, this one. Okay, and then O2. So now we write the whole rate constant as a new constant, which is K. So we get NO2, NO squared multiplied with oxygen concentration, which is in agreement with the postulated rate law. Now this is the second set. Okay, second set. Step 1 is fast at equilibrium, followed by step 2, a slow step. Okay, so step 2 is slow step, so we write the rate law based on step 2, which is this. Okay, K2 NO OO NO. Okay, again OO NO here is not in the overall reaction, so it is an intermediate which shouldn't be in the rate law. So we have to replace this using the first step, which is the fast step. Okay, so from step 1, okay, this has been simplified for you. Okay, so OO and O equivalent to K equilibrium and OO2. So we substitute this, okay, into the rate law expression from the slow step. Okay, so we get K2 and O here. Okay, K2 and O here. Okay, and then substitute this here. Okay, we have 2 and O now, so that's why you get squared here. Okay, and then O2. Okay, and then this K2 K equilibrium can be changed to a new equilibrium constant, which is K. So we have K and O squared O2. Still the same rate law, but different set of mechanism. Now this is the case where there are more than 2 elementary processes, and one of the elementary processes is is a slow step. Must have at least one slow step. Okay, example is hypochlorite iodide reaction. Okay, so this is the overall reaction. This is the rate law. Okay, note that it's not in agreement. Okay, the rate law is not in agreement with the overall law, overall reaction. Some cases you have the agreement between the rate law and also the overall reaction. So these are the possible reaction mechanism for the hypochlorite iodide reaction. So 3 steps. Step 1 is fast equilibrium. Step 2 is slow rate determining step. And step 3 is fast. So the first step that we need to do is to write the rate law based on the slow or rate determining step. Okay, so this is the rate law. Okay, K2, because it's step 2, so K2 I minus HOCl. Okay, so looking back at the proposed rate law, okay, HOCl shouldn't be in the expression, so we have to replace this. And how to replace this? using step 1. So it has been simplified here. Okay, K equilibrium is equivalent to HOCl OH divide with OCl H2O. Okay, so we substitute HOCl. Okay, so let's say we keep the HOCl here. Okay, so we have K equilibrium multiply with OCl minus and also H2O. Okay, and divide with OH minus. Okay, so we substitute this, okay, into this. Okay, so we have OCl I minus over OH. Okay, this is new one. Okay, after substitution. So if you look here, it is still not in agreement. It is in agreement with the red law, so we don't have to do anything else. So means we don't need to use step 3 to solve this problem. Okay, if necessary, then we use step 3. But if we use step 3, there's no k minus 3. It will be k3 only because it's only one direction. Unlike this one, step 1. Okay, it's equilibrium both direction. This is another example involving more than 2 steps mechanism. A reaction between carbon monoxide and chlorine to form phosgene. Okay, so this is the balanced chemical reaction from the 3 steps here. Okay, and then this is the red law expression for this reaction. So if you notice here, step 1 and step 2 are both fast and at equilibrium. Okay, the arrow are pointing at both directions. Okay, and then step 3 is a slow step. Therefore, we need to deduce the red law based on the red determining step, which is the slow step. So first of all, we write the red law according to step 3. Okay, so this is the red law. Okay, the rate of formation of phosgene over dt is equivalent to K3COClCl2. Now, if you notice, COCl here is the intermediate. It's not shown in the overall reaction. So therefore, we need to replace this or substitute this according to the step 2, because step 2 have COCl. Okay, so this has been simplified for you. Okay, K2 over K1, okay, K2 over K negative 2, COCl or over Cl multiplied by CO. Okay, so we bring this over here, so we have COCl equivalent to K2 over K negative 2 multiplied with Cl CO. Okay, so we substitute this into here. So we have K3, K2, K negative 2, Cl, CO, Cl2 from here. Okay, so if you notice, it's not complete yet. That's why we have Cl, which is not present in the overall reaction. So we have to replace that. So in order to replace that, we use elementary step 1 because it has Cl here. Okay, so we rearrange this so that we get Cl. So we K1 over K negative 1 multiply with Cl2, and then this one is Cl squared, and we don't want the square, so we bring squared over here, so it's square root here. So we substitute this into here, so we have K3 K2 over K negative 2 square root K1 over K negative 1 Cl2, so I write here fraction, square root CO and Cl. Now we combine this and this, we get, we convert all of these equilibriums into one constant into one, so it becomes K. So K Cl2 3 over 2 CO, which is the red ball. Okay? Yeah. This is another approach to solve reaction, a red law based on the reaction mechanism. A reaction where all the steps have comparable rates. So the steady state assumption can be used to obtain a rate expression from the mechanism. So the steady state hypothesis assumes that the concentration of very reactive ingredient remain very low and effectively remain constant compared with the reactant concentration. So the steady state approximation therefore can be applied to the thermal decomposition of nitrogen pentoxide where all the steps have comparable rates. So what does it mean? Okay. So we have the decomposition of nitrogen pentoxide here. Okay, a first order reaction. Okay. Note that the red law is not in agreement with the overall reaction. Okay. 2D. Okay, the red law is first order. So this is the proposed mechanism. Step 1, step 2, step 3. Earlier on, I've shown you using the slow steps and then include fast at equilibrium. So fast reaction into solving the red law. Okay. So this is another approach. We use the steady state approximation. How are we going to do that? So we identify first the intermediates which are not in the overall reaction. In this case, they are NO3 and NO2. Okay, because their concentration is very small, it can be calculated by steady state approximation approach. Okay, so the expression involving NO3 here, dNO3 over dt will be equivalent to 0 because too small. Okay, so we include NO3 from steps 1, 2, and 3 because all of the 3 steps have NO3 in it. So you have to write the expression here. Okay, so K1 and O5 because it's fast and equilibrium. So negative K negative 1 and O2 and O3. Okay, minus K2. Okay, only the first one Okay, is positive. The rest you will see negative. Okay, so minus K2 NO3 NO2 minus K3 NO3 NO2. So these are all the reactants in step 2 and step 3 respectively. Okay, so next what we do, okay, is to bring the expression with NO3 to one side. Okay, it's not shown here. Okay, so means from this, let me use other color. This onwards, okay, this part onward until this part, okay, we bring it to this side because it's 0, right? Okay, so we bring it to this side. Okay, so when you bring it to that side, we'll have K, 1, 2, 3, plus, because we bring to the other side, so it becomes plus K2, 3, 2, plus K3, NO3, and O, leaving behind K1 and 2 or 5 on the other side, okay, on this side. So now, because K negative 1, K2, and K3 all have NO3, so we bring NO3 here, outside, okay, outside. Let me use another color. So we have NO3, so we put NO3 outside. So in bracket, K negative 1, NO2, plus K2, NO2, plus K3, and O. So it equals K into O 5. So now, close this bracket. So now, leaving behind NO2 on this left side, we bring this here back to this side. So that's why you see here K1 N2O5 divide with K negative 1 NO2 plus K2 NO2 plus K3 NO. Now we do the same for NO intermediate. Okay, so look at the step having NO. So in this case, NO is present in step 2 and also step 3 only. So we don't put step 1. Okay, so the red law expression for NO is 0. Okay, K2, okay, remember the first one will always be a positive value. Okay, and then minus K3. Okay, and now we bring NO like we did for NO3. Okay, we leave it on one side, so we leave this NO on that side, and we bring this, all of these, to the other side, to the other side, okay, to the other side. That's why we end up getting NO equals to K2 over K3 multiply NO2. Now what we do next is substitute NO into NO3, 2 just now, okay, into 1. Okay, so when we substitute 2 into 1, okay, so we write back 1 just now, which is NO3 equals K 2O5 divide with K negative 1 NO2 plus K2 NO2 plus K3 NO. Okay, so 2 just now is NO equals K2, so this one is right. Okay. So K2 over K3 NO2. Okay, so we substitute this 2 into 1. Okay, so look for NO. So we have NO here. Okay, with this other one. So NO here. Okay, so we substitute this here. Okay, so that's why we end up getting K1 N2O5 divide with K negative 1 plus 2K2. So now this become K3 multiply with K2 over K3 just now, right? When we bring this over, so we can cross K3. That's why we have K2 here. So now becomes 2K2. 1K2 here, another K2 here. So 2K2 NO2. Okay. So the reaction rate is given by the production of oxygen, okay, which is this. Okay. So we substitute NO3 here, okay, into here. Okay. So we get K2, K1, K2, N2O5. This one is now. This one. So we have K1 here. Okay. Now, okay. So K1 here and K2 here. So we have K1, K2, okay, N2O5. And this N2 is put at the back. Okay. So substitute NO3 here. So we have this here. Okay, this one. Okay. So here, here. Okay. So we simplified. Okay, we simplify this. So we get K1, K2, and 5 divide with K negative 1 plus 2K2. Okay. So now, because we have all these K's, we can substitute it with a new rate constant K. So we get K and 2 or 5. So because this one just now divide, right? Divide. So this one is here. Then multiply NO2. That's why you cross NO2. So this is the red law solving using the steady state approximation. So you have two options, either to solve reaction mechanism rate law using the rate determining step, or you use the steady state approximation. Either way will do. Okay. For my personal opinion, it's easier to use the slow step, rate determining step. Okay, because you can easily do silly mistakes when you use steady state approximation. So that concludes the kinetic lecture.